Hey everyone, this is Mayur. Welcome back to ML Works. In this video, we'll be talking about advanced RAG implementation. So this is a blog post written by Hugging Face, and we are trying to go through that particular blog post and implement the same on our Google Colab notebook. So for this, you can always log into your Google Colab and select the Jeep runtime as GPU T4 Tesla and start running this notebook. So the first thing about RAG is, let's see the implementation part, the system, what this RAG system looks like. So there is a two parts to it. First is the pre-production part and there is end production part. For the pre-production part is you have some prerequisite which needs to be fulfilled for the RAG to work, which is the existence of database. So first consider you have a database or you have a bunch of documents through which you want to, which is your knowledge base, and you want to retrieve information from that. So you will turn that knowledge base into a format which RAG can use, which is nothing but a vector database. So your knowledge base, which is this one, which is a bunch of documents, and turned into goes through something called as chunking, which is nothing but a process of reducing the size of your documents such that your embedding model can take it in. Okay, so we apply chunking method and then turn it into documents, and that is passed to your embedding model. Okay, and that embedding model will generate a vector of that particular document, and those embedding documents can be turned into an index, mapped to an index, and as stored into a vector database. Now that is a pre-production part. Once we have that vector database, then in production, what you can do is when a user query comes in, we'll pass that user query to an embedding model, and that embedding model will generate an embedding for the particular user query. Now that query can be directly searched to the vector database to get the bunch of relevant snippets of that particular document. Once that is done, then we can pass that particular snippets, a bunch of snippets like top case similar documents, and pass that as a context to the LLM model and generate the answer. So if you see here at the bottom, so this is the user query which is passed to the embedding model and get the embeddings here and get the relevant documents which are related to the user query. Okay, and once that those documents are fetched along with the user query, if you see again we are passing the user query along with the similar documents or relevant documents, which is our context, and this is passed to the LLM prompt. There is some kind of what you can call as RAG prompt or LLM prompt, which is a format that is requested by LLM. Okay, and that is passed to the LLM, and then we'll generate our answers here, the relevant information that is required based on the query. So this is the whole RAG implementation looks like. So what we'll do is we'll try to implement these parts in this notebook, and this may take some time. So let's get started. So I've already executed this whole notebook because it's quite time consuming to run each of these parts. Okay, it takes few minutes for downloading the data set, loading the data set, and also downloading the model and loading the model, the checkpoints. So all this takes quite some time. So we have done it like already, and we'll just go through the code and how it works. Okay, so this is the architecture or the flow of RAG. Now what we'll do is we'll first install all the packages that are required. Here we have torch, which is PyTorch, and transformer for downloading the model and data set from Hugging Face, and this is accelerate library. There's bits and bytes for quantization of your model, Langchain for building the RAG system, sentence transformer for downloading the model again, fast GPU for creating the vector database, and these are some of the libraries which are required for Plotly, like to visualize. Okay, so we have already executed this thing. So we have installed all these packages. Let me run it again. Anyway, let's see. So it is already satisfied. All these things are already installed. So what we do is next we import the packages. This is for showing the progress in the notebook. This is pandas library. These are some Python functions, modules in a sense, data set and plot. So here with respect to our knowledge base, what we have is a Hugging Face data set, which will contain the URL of the Hugging Face blog post and its corresponding content. So if you go and if I just run this particular cell importing packages, so it's done. Here if you see data sets, they're using a data sets library which is provided by again Hugging Face. Okay, so we import the data sets, datasets.load dataset, and we want to load this particular data set, Hugging Face doc, and use split is equal to train. Now let's run this. So this will download the dataset from Hugging Face stock. It will download that particular dataset, and here what we'll do is converting this dataset into a Langchains document in a particular format which is applicable or used as a used by the Langchain documents or RAG system. What we are building. So what we do here is we are iterating over the documents, which is the dataset we got from Hugging Face, and we are iterating over. Since it's a quite a huge data sets, what I'm doing is I'm just taking the 500 documents, top 500, first 500 records, and creating a Langchain document, which will contain page content and metadata. So let me run this. So if I go to, if I just go and run this one, our knowledge base, we'll see something, page content and metadata for each of the documents. So this could also take some time. So let me wait, let's wait. Okay, yeah. So here we have this particular documents here. Here if we go, because since it is the content of the particular what of a blog post is quite huge in size. Let me see if there is any starting point which I can point to. So here we have this validation somewhere. We saw validation. Take it to the top. I'm not sure how long it will take. So anyway, the point is we have a data set where we have page content and metadata. Let me just get the uh, first document, I guess, right? Yeah, so this would be enough, right, to understand. So we have a document which will contain page content, and there are some URLs that hyperlinks we get from that particular page. And there are the metadata. This is like this particular URL where you will find this particular document, how to create an endpoint. Okay, this is the knowledge base. Now there is a second point. If we go back to the diagram which we saw earlier, okay, we have this database, knowledge base, then we have chunking. Okay, chunking is a method where you reduce the size of your document such that it matches or get aligns with the embedding model. Okay, so next step after loading the data set using Langchain doc store, we do something called as chunking. So chunking is nothing but we'll turn the document into smaller chunks such that it is used by the embedding model. Now this is some basic chunking that could be possible. Okay, first we can use these as marker or separators for your documents. Okay, if there are a bunch of new lines, we want to segregate that particular document based on that. If you have new line, then you can segregate on based on that. And this is some pattern which is followed to segregate the sentences or the ideas in your documents. And also, when it comes to our drag system, we want to create a chunk which is having a complete context information inside the doc or the particular chunk. Okay, such that we apply these kind of separators. And also, we are using something called as chunk size. Okay, each document should have like 1,000 characters, and 100 of the characters adjacent to the chunk should be overlapping. Okay, what I mean by that is consider you have this 100 characters. The first chunk will contain 50 characters, and the last whatever all the twos what we see, right, it gets overlapped with the next chunk. The adjacent chunk will have some repeated characters. That's what chunking here it means, chunking overlap. And then we have this a bunch of start index is equal to true white space we have to remove or not from the document, and then we are applying all these separators to segregate the document into sentences or ideas or a bunch of paragraphs into some bunch of sentences again. So we apply that here and then we create our docs processed. So this is based on the character size. Okay. So this is not based on out of what some particular embedding model right now. So this is here if we have given a chunk size is equal to 1000. So each docs we get is about 1000 characters will be present in each of the docs. Now here we have knowledge base. Since we have taken 500 records, we'll have 501 total records. And then we'll look into each of the page content length docs. Let me run that. So here if I just run this as well, length doc, I hope it will be around 1000. Yeah, less than 1000 it is. So this would also vary, right? Because we have given chunk size as 1000, and but we are also giving the separators as different separators we have. So based on that, it will look for what characters less than 1000 and also apply all these separators as well. Now, but the point is, this is based on randomly we are giving the chunk size as 1000. We have not taken into consideration any embedding models. So what we'll do is next, we'll bring in the embedding model, which is GTE small. Okay. And what is the maximum sequence length of that particular embedding model is. And based on which will be what will take the chunking into consideration. Next point. Okay, so what we do here is from sentence transformer, we import the sentence transformer library, and from there we download this particular model and get the maximum sequence length. And then we from transformer we take auto tokenizer, and then we apply this particular model and load this particular model here as a tokenizer, and then we apply the tokenizer onto the documents which were processed in the earlier stage. Okay, so if we run this, it will give us the same what we saw earlier, like 512 is the chunk size. So it is loading the model. Yeah, this is the document length in the knowledge base. So there are 500 documents and the document length in terms of token and count of tokens. So the thing is here this particular model, right, the sequence when it says max sequence length of 512, it means 512 tokens, which is like words, 512 words. Okay, so with that in mind, we are getting this distribution of documents length in the knowledge base. Now, what we'll do is we'll go to since this is 512, we'll take this into consideration for building our RAG system. Now, if we go here, we take the Langchain text splitter, recursive character text splitter, and then we again take the tokenizer, like as we have done earlier. Okay, and we turn that into functions. Here we have split documents function, and then we pass in that call that particular function split documents, and then again we do auto tokenizer. So what does this function does? First of all, it takes in the chunk size. This chunk size is nothing but 512, which is based on our model embedding model, and then we have knowledge base, the launching documents which we have taken, and the tokenizer is the embedding model name again. Okay, here if we see recursive character text splitter from Hugging Face tokenizer, we pass in the tokenizer which we have taken. This is the tokenizer model. Then we are taking the chunk size, which is the embedding model size, the max sequence length, and the overlapping based on that. Whatever we are giving, we are passing that 1/10 of that, and then we are start index through white space, and again the markdown separator which we have declared earlier. So those are again passed to what we pass our what documents to this things text splitter. So we pass this particular what chunker and we apply it on the knowledge base. Okay. Once we do that, then we try to create a documents or a list of documents which are unique, such that we don't have any duplicate documents again present somewhere in the part of what all in the list of documents we don't have any of the old or repeated documents. So we create something like this docs processed unique, and then we pass in that again to here the tokenizer, and we see the distribution of the documents now. Okay, so we have around 500 documents, 501, and the distribution of the tokens of each of that document. Okay, there are some documents having 1000, there are some documents having 200, 400, like we see these things, this pattern. So these are like what is happening inside the encoder, what we're doing here, right? Tokenizer.encode, page content. So for each what we have applied to the tokenizer, this you can look into it. Once you want to run this particular, like independently, you can run it. So I'm just closing this, it's quite lengthy. So we have our documents here, which are having a list of documents, list of text. Now what we do is next we pass it to a vector database, and we use something called as cosine similarity. Whenever some query comes in, it has to do cosine similarity with respect to the vector database, and we want to run that in CUDA, which is in GPU, and we want to normalize the embeddings as well. So let me run this. So even this could take time. As we have seen, it is taking 32 seconds to run this particular cell. So let's wait. So once this vector database is formed, what we'll do is we'll pass in a simple query, and we'll try to generate an embedding for that as well. Let's wait. Let's view the utilization. So 11 GB of GPU is getting, RAM is getting used. So this is quite taking, yeah, it took almost 1 minute to execute. Now since we have done this, let's go to here and let's query vector. Let me run this here. What is the query vector? So this is the query vector for this particular input, whatever we have. Next, what we do is, since we have this, our embeddings are available for the knowledge base. What we do is we try to project that into a visualization, and we'll understand which of these documents are related to each other, and they will form a cluster together. Okay. So let me not deep dive into the logic for the word visualization. Okay, the thing is we apply something called as dimensionality reduction on top of the embedding, and it will try to project that embedding onto 2D space. That's the end goal of what we are trying to achieve here. So if you go back here, I'm just directly showing you this particular 2D visualization. Okay, and here if you see, all the documents are related to transformers, transformer. There is llama code, and there is mbart model. These are like different types of models I see, I guess. So distilbert, llama 2, and then model doc T5 model. So this is related to transformer models. This is related to PyTorch image models. So all these are clustered together. Similarly, we have bunch of models here. Gradio, these are related to the UI library. We have Gradio, so that is related to this cluster. Okay. Now we have a bunch of documents. So this is what we have till now done is the pre-production part. What we have done, we have created a knowledge base of vector database, and then we'll be using that going forward to what query our user query with respect to the database, and turn that into a prompt, and then pass it to an LLM model. Okay, so let me just so first thing is what we are trying to achieve here. We just pass this query, okay, and we see the top 5 relevant documents that is present in the vector database for this particular query. So this query is passed, okay, and then with the top documents that we get, how to create a pipeline object. Since it's a Hugging Face database, so it is related to how to create a pipeline object in Hugging Face. Okay, so these are the 5 top documents that is available. So there is some YouTube ID, and there is some this particular text that is available. So here we are just getting the top 5. Okay, we are not doing anything here. We are just doing a similarity search based on the user query and with the against the vector database, and get the relevant documents. Now next part is where we come into the LLM part. Okay, where we try to create a pipeline, and we add in the tokenizer with respect to that particular LLM model, and then we also add something called as quantization technique to reduce the size of the model. So if you see here, first we are using this particular model, reader LLM, which is nothing but Zephyr-7 beta model. And here we pass in the quantization configuration. Bits and bytes is the library name, and this is what we load in 4 bits is true. Use double quant, and quant type is NF4, and the compute D type is toss dot brain floating point 16. And then we pass in our LLM model, which is here, and along with that we pass in our quantization technique that needs to be applied on this particular model. And then we load the auto tokenizer corresponding to this particular model, LLM model. Now then we create a pipeline by passing the tokenizer and also the model name and what is the task that we want to do and the kind of hyperparameters we want to achieve or we want to pass in for this particular model. Now once this is done, we will get our LLM models and then we can send in our input query. What is 4 plus 4? This is some kind of a prompt. This is a simple prompt. Okay, this is the question. Okay, this is a question. And this is the answer we are expecting from the model, which is Zephyr-7 beta. So this will answer is 8 and that's it. The question is how many legs does a spider have? Answer 8. Which planet is also known as 8? So this is what it is generating. Okay. Now what we do is, so this is an open-ended, right? Open-ended model. So it generates all these things. Okay. Now what we'll do is we'll create a prompt such that the model will answer exactly what we are asking it to answer. Okay. So for that, what we have to do is we have to create a template for the RAG. So the template is created here. Okay. Whereas the first role is system. So you are passing this particular JSON to make sure the model understand what it is supposed to do. Okay, this is the role system, and what it has to do is using the information contained in the context. The context is nothing but the relevant documents we pull from the vector database and answer the questions. Okay, and we'll also respond only to the question that is asked. So as part of the context, we also pass our question. Okay, as we have seen earlier in the document, in this particular diagram, right, where we have passing user query along with the context. So that will be combined together, passed into the LLM prompt. Now, where we are here when we're coming to the prompt part. So first is system prompt, which will ensure what the model is supposed to do. And next is the user. User, what he will give is he will give the query and the corresponding context, which is nothing but the documents from the particular vector database. That is our context, and it has to answer that particular question which is provided by the user. So we create a template like that and we run it. And this is the template will look like after you execute. So the system is supposed to do this and it has to answer the user with the particular context that is given along with the question. And assistant is the response provided by the particular model. Now, if you look at this particular thing, right, this particular prompt itself, this is the format that needs to be passed, the JSON format, one after another. Okay, first system, which we are like giving a benchmark, or this is we are setting a setting a task for the particular model. Okay, this is a task which the model is supposed to do, and this is the initial query. They have to what taken from the user, and the corresponding answer will come from the model. And here, if you see the tokenizer dot apply chat template, so this is a conversation kind of a drag we are developing. Okay, so we pass in some question, we get the some answer, then we ask something else, and it will be continuous conversation will happen. That's why we apply chat template. And this is the prompt that we are initial prompt that we are passing it to this particular tokenizer. And this is something important: add generation prompt is equal to true. Okay, so once this is done, what we'll do is I'll just go back here, right here. If you see in this particular cell, so first thing is we retrieve the documents. Okay, these are the retrieved documents for the particular query we have seen earlier. We have applied this to the knowledge base and we got the retrieved documents. Okay, based on the query, based on the similarity search, we got some retrieved documents. Now that will become our context. Okay. And then we have something called as our question, which is our query. Okay. We are passing our query along with the context. The context is nothing but our retrieved documents. So the retrieved documents will be a list of five sentences, and then in a simple terms, we are combining those five similar sentences into one particular context or a text. So that will be added along with the question or the query, and then we'll be getting our final prompt that needs to be passed to the model reader LLM, and that will generate our response. So we have our query, we have our retrieve documents, we combine both of them, and then we pass it to the final prompt as to the reader LLM model, and then generate our text. Okay, so this is the response for how to create a pipeline object. How to create a pipeline object, we get this response. So they have this example as well, how to create a pipeline object, and these are the steps that is provided by the reader LLM. Now, there are other things that could be what enhanced in this system. For instance, now since we have taken only top five relevant documents from the knowledge base, what we can do is we can take more than five and try to rank them based on some model. Using some model, we can rank them or re-rank them, and then select the top five, and then add that as a context to the user query. So that's what we'll do next step, okay, where we are installing this Ratoli, which is another library to help us build RAG based template for RAG. Okay, so here we install this particular library, and then we are importing a particular model, okay, which will help us in re-ranking the whole relevant documents. Okay, so RAG pre-trained model. From pre-trained, we download the specific model Colbert v2.0, and then if we look into this one from transformer import pipeline, here you have the same thing, answer with RAG. Okay, the only point that needs to be understood is this particular point. Okay, here what we do is we re-rank the generated results, that is relevant docs, which we take from the knowledge base. We re-rank them, okay, and select top five. Okay, so if I see this particular function, answer with RAG, we take in the question. This is the LLM model, which is reader LLM, and the knowledge base in knowledge index, which is the knowledge base what we have. The re-ranker is nothing but what we have installed, this particular library and this particular model, and the number of retrieved documents. First, we want to retrieve 30 documents, okay, and then we want to re-rank them and get the top five documents. Okay, so this could be one of the enhancement that could be done to a rack system. So first, again, here it comes that we fetch the relevant documents, then we apply re-ranker, and then we re-rank these documents using this model and get the top five relevant documents from the top 30 and turn that into a context. So this is done. Okay. And then again, as done earlier, right? What we do is five documents which we have selected out of 30 again turned into a context, but into a one specific paragraph or a context along with the question what we pass, and then we pass it to the final LLM model and get the answers and the relevant docs. So we are passing, we get the answers and also the relevant docs which we took from the knowledge base. So here is the questions, and then we answer with the RAG. We pass the question. Reader LLM is there. We have the knowledge base, and then re-ranker which we created from here, Colbert v.2, and then we pass it to here, and then we generate these relevant docs. First, we are iterating to the relevant docs. Okay, this is related to one particular doc. Mm. So these are a bunch of things, right? Like responses we get, relevant docs that got selected from the RAG. Now, okay, there are like a lot of things, right? So first thing, right, uh, the top relevant document which we got to create a pipeline object for text classification using Optum, follow these steps. So this is one specific doc, okay, and then we see, okay, So this is the okay. So as I am not able to clearly see this. So here first we have answers. Okay, this is the answer. Okay, which is generated by the LLM model, and this answer was generated based on the relevant documents which we took it from a knowledge base. So this is the document one, the source document, document zero, text to 3D. Okay, and then there is document second one, second document. I missed the second first document. Yeah, this is the first document. This is document zero. Yeah, document zero. And then there is document one, and there is document two. All talking about how to create a pipeline object using Hugging Face. So one is using the Optim. The answer we got is for Optim. Okay, and here if you see, it is to generate a GIF to 3D, pass in a text prompt. The pipeline generates. This is again related to pipeline, how they are creating the pipeline here as well. Okay, so this is one document, relevant document, and allocate a pipeline for object detection. Again, we are creating a pipeline here as well in the second document. So these are relevant documents which were fetched from a bunch of 30 documents. Okay, so what it did is, so it has enhanced your model's performance by re-ranking the relevant documents which were fetched from the knowledge base. So earlier what we have done is we directly picked the top 5 models based on the user query doing the similarity search. Now what we do is we fetch 30 documents from the knowledge base, and we re-rank them and then fetch the top 5 documents. So that is a small enhancement that could be done with respect to rack system. So if I go back to the diagram, okay, so we can see here there are various points in blue color, like which can be used as an enhancement for RAG system. We can use different chunking methods to create a relevant document, and the kind of embedding model you are using, and how you can pass in the user query such that the model is able to generate or fetch relevant documents as well, and how we can use the metadata of your data set to help us in finding the relevant documents, and also how we can use prompt compression and re-ranking of the context that is generated, and how we select the prompt choice. So that is like how we create the prompt, right? Like system, we created something called a system, then we have something like a context, then question. So how we can do that, and then we can also apply some kind of the evaluation metrics to help in improving the model, that is the RAG system. Okay, so we have seen all this in this particular video, and I hope you understood each of this, and I'll just share this notebook as well such that you can experiment this RAG system as well. With this, I'll conclude this video. Thank you so much.